Saturated solution means the solution point at which if you add further amount of solute, it is giving precipitation. Further amount of solute is not soluble in the solvent and giving what? A precipitation. So the solute behind which it is dissolved, that is called what? Saturated solution. Further, if you add, what happen? It will give precipitation and become unsaturated solution, isn't it? That means what happened? Sorry, I'm saying about unsaturation, the saturation like this. Now this is unsaturated bed. Sorry, I want to explain this one by taking this example. Unsaturated, saturated bed. Now here it is solvent is there. You are having some solvent is there here. This is a solvent. Now you are adding solute. You are adding solute. Now it is dissolving here. It is dissolving. This is called unsaturated. Now again, after addition of some solute, you got a solution here. You got a solution. This is solution bed. This is a solution. Now adding solute here. You're adding solute to this one. Now if you add solute, what happens? It's giving some precipitation like this. Giving some precipitation like this. Now it is called what? Saturated. If it is not giving any precipitation, the solute is easily soluble in solvent, then that is called unsaturated. Unsaturation means we can add solute to get the solution, right? But what is saturated solution? When you add further amount of solute, it is giving precipitation. So that is called what? Saturation. So what I mean to say is that how much amount of your solute you are adding in a specific amount of solvent to make the solution into saturated solution. That means further solute you can't add here. Maximum amount of solute we can add to solvent to give saturated solution is nothing but called solubility here. So you may get for 1 mark question, what is the meaning of solubility? You just make a definition in your own words like this. Next, if you observe, what are the factors involving in the solubility? Which factors will involve in the solubility? First of all, the nature of the solute, nature of the solvent, temperature, and the pressure here. 4 conditions are there which can influence the solubility. Nature of solute and solvent, temperature, and the pressure. Let me see each and everything. Then, first of all, we'll see the solubility for solid in liquid here. Solubility for what? Solid in liquid. That means you are adding some salt in liquid, water. What will be the factors which are affecting it? So solubility of solid in liquid. That means you are adding a salt in water. Just imagine this is a water. This one is a salt. In this case, what is the effect now? We see first nature of solute and nature of solvent. First of all, we'll see like dissolves like. In chemistry, we always say what happened, like dissolves like. Means what happened? Polar will dissolve in polar, non-polar will dissolve in non-polar. That means what happened? Polar solute will dissolve in polar solvent. For example, NaCl I have taken. I am dissolving in water. NaCl I am dissolving in the water. NaCl is what actually here? Polar. Water also what? Polar. Now it will soluble. But it's the same NaCl if you want to dissolve in benzene. Is it possible better? Is it possible? NaCl in benzene is possible? Why not possible? Because benzene is non-polar. So it is never possible. So what they are saying, polar solute dissolve in polar solvent only. So like this here. But not like this, never happens here. Next, non-polar solute dissolve in non-polar only. Isn't it? Non-polar solute will dissolve in non-polar solvent only. For example, I will take from something CCl4 I am taking. Dissolving in benzene definitely will take place because both are what? Non-polar. Both are what actually? Non-polar. It is a non-polar and it is a non-polar. Now they can dissolve. That means like dissolves like. If you remember like dissolves like, it will be easy for you. Next, effect of temperature. The solubility of a solid in a liquid affected by temperature. Everyone knows this one. If you heat, what happens? Definitely what happens? Solubility will increase. Everyone knows this one. So the enthalpy change in the solution is denoted by delta X. Delta X means what? Enthalpy change for solution. So whenever if you are dissolving, what happens? A salt in the water, effect of temperature, we are considering in the form of enthalpy change in solution. If the dissolution process exothermic, here two things you have to remember, beta. It's very, very important, beta. This point is important. It is not a general topic. It needs some principles. According to Lee Chartered principle, we'll explain this one. Now let me see endothermic process. What is the meaning of endothermic process, beta? Anybody? Endothermic process.
Which consumes energy.
In this process, it will energy will be or heat will be absorbed. Simple thing, it is energy consumed or heat is absorbed. Endothermic process. For example, I have taken ammonium chloride, I have taken NH4Cl, I have taken. I am dissolving in water. Dissolving in water like this. Now in this case, energy is absorbed, delta H equal to positive. Delta H equal to positive, heat is absorbed. Heat is absorbed. Right? Endothermic process, this process. In this case, the solubility increases with rise in temperature. When that means what happened for all endothermic process, in which what happened, heat is absorbed. For them, if you heat this one, when you heat this one, what happened? With respect to temperature, solubility also will increases. Because the process is what actually? Heat is absorbing here. Okay. Now when you heat, what happened? Equilibrium should what happen? When you heat, when you are supplying the temperature, when you are supplying heat, what happen? Equilibrium should what happen? To decrease the temperature, it will shift into what? Decreasing side. In which direction temperature will decrease, beta? Endothermic. Understood my point here? You are heating this one. Listen carefully, you are heating this one. Whatever you do, equilibrium you do in opposite direction. Isn't it? Understood my beta? If for example, a husband asks wife what happened, bring coffee. Wife say what happened, wife will bring tea like that. Because she will do what? Opposite. Whatever husband say what happened, wife do what happened? Opposite. Same thing like that here. When you heat, the reaction, the equilibrium reaction will do opposite here. So when you are heating, what happened? Now equilibrium should decrease this heat. It should decrease this heat. How it will decreases? By absorbing the heat here. How do you decrease the temperature, beta? What is the point? How you can decrease the temperature? What is the possibility? How do you decrease the temperature? By just absorbing only, no? So when you heat here, equilibrium, isn't it, should decrease the temperature here. In that case, it will absorb the heat. In which direction heat is absorbing? In this direction. When ammonium chloride is dissolving in the water, heat will be absorbed. So more ammonium chloride will be absorbed here. Understood my point? Again, I am saying in one sentence here. When you are applying the heat, isn't it? The temperature is increasing. Now equilibrium should decrease the temperature, decrease that heat. In that case, equilibrium will dissolve more ammonium chloride, which is what? Endothermic process, heat will be absorbed. Right? So this is about what? Endothermic reactions. So for endothermic reaction, single line I am saying, for endothermic reaction, the solubility will increases with respect to temperature. Right? Next thing. For exothermic process, that means what happened? Heat is releasing. In this case, I have taken sodium hydroxide pellets. I have taken sodium hydroxide pellets. You have seen in the laboratory, I think, many number of times. Sodium hydroxide pellets. That means solids dissolving in the water. Dissolving in the water. This process is called what? Exothermic process. Whenever if you take a beaker, into that take some water, specific amount of water, add some NaOH pellets into this one. Immediately the beaker becomes hot. Immediately heater become whatever the beaker will become hot because it's exothermic reaction. So whenever if you take exothermic process, the solubility will decreases with rise in the temperature. Why? Because see, you are heating here. You are heating here. Correct or not? You are heating this one. Now, when you heat, equilibrium should what? It should do actually, but equilibrium should what? It should do? It should decrease the temperature. Correct or not? It should decrease. Now, equilibrium should decrease the temperature because you are heating. Equilibrium should decrease the temperature. Now, when you add NaOH in water, exothermic process, temperature is increasing or decreasing beta in this process? In this process, temperature is decreasing or increasing? NaOH adding with water.
Decreasing.
When you add NaOH in the water, temperature decreases or increases beta?
Increases.
Some saying what increasing, some saying decreasing. Which one is correct beta? Addition of NaOH in water is exothermic process. In exothermic process, heat will be released, temperature will increases. So addition of NaOH in water, temperature will increases because it is exothermic process. Then you are heating this one. When you heating this one, equilibrium should decrease the temperature. But when you add NaOH to the water, temperature is increasing. So what happens here? Reverse takes place. Reverse means what happened? Solubility does not take place here. Reverse to solubility takes place. That is the reason when you, isn't it? When you increase the temperature, solubility is decreasing. You have to avoid the confusion, leave it this confusion. Simply say what happened for endothermic reaction. For endothermic reaction, solubility directly proportional to temperature. Directly proportional to temperature. For exothermic reaction, solubility, isn't it, inversely proportional to temperature. That's it. So this is the effect of temperature. Ammonium chloride dissolving in the water, endothermic process. For that one, directly proportional. Sodium hydroxide dissolving in the water, exothermic process, inversely proportional to temperature. Next, generally the solubility of solid solutes in liquid solvents increases with rising the temperature. General phenomena if you observe, most of the salts, when you dissolve in the water, their solubility will increase with respect to temperature. Only few salts are like that, in which it is what? Like that. Next, NaCl solubility is not much affected by increasing of temperature. For example, if you take what happened, NaCl in water, even though if you increase more temperature, what happened? NaCl solubility does not increase much because NaCl is completely solved in the water in normal conditions only. Normally, it will give saturated solution only. When you heat, what happens? Water will be evaporated, and your only the solute will be strikes on the water boundaries of what? That container actually. Now let me see what happened here. Different type of temperatures I have taken 0, 20, 40, 60, 80, 100 degrees Celsius I have taken. And solubility of different type of solutes I have taken here. This is a solubility increasing here 50 to 250 grams per what happened liter. The solubility increasing here. Now when you observe for NaCl, not much difference you are getting. 20 to 100 degrees Celsius what happened? There is no change in the solubility. KCl you observe what happened? Increasing. Okay. KNO3 if you observe what happens? Study steeply it is increasing what happens? Straight line you are going to get like this. It is increasing. KBr increasing. NaNO3 increasing. NABr, isn't it? No change in this case. So some of the salts what happened? They are not much changing with respect to temperature. Some of the salts what happened? Readily what happened? Getting more solubility with respect to temperature, isn't it? Now if you observe what happened, Na2SO4, it is increased. Then what happened? Suddenly what happened? Decreasing after 20 degrees Celsius. Of 30 degrees Celsius, it is what happened? Decreasing here. Means because of what? Endothermic process. Because of endothermic process, what happened? It is what happened? Decreasing here. So whichever the salt, remember, whichever the salt dissolving in water, if it is endothermic process, definitely what happened? They decreases here. Next, what happened? Effect of pressure. Effect of pressure. Pressure does not have any significant effect on the solubility of solids in liquids. So there is no effect. Generally, what happened? Effect of the pressure. because solid and liquids are less compressible when you compare with gas. So if I take what happened a gas here, this is a gas here. When you compress this one by using a piston, by using some weight over here, take some weight here, compress this by just press this one, gas will compress here. Because of high pressure, what happened? Gas definitely will get compressed like this. It will definitely will get compressed like this. So gas will affected by what? Pressure, but not solids. If you take what happened a solute in the form of solid state, even though if you take what happened at high pressure, this solute in the form of solid state does not affect with their pressure here. So even if liquids also what having very less effect over what happened pressure actually. Next, if you see what happens, types of solutions based on the solubility. What type of solutions we are having? Just now I told you, no, saturated, unsaturated, supersaturated. Three types of solutions are there: saturated, unsaturated, supersaturated. What is saturated solution? A solution in which no more amount of solute can be dissolved at the same temperature. But if you increase the temperature, what happens? You can further solubility can takes place. But without changing the temperature and the pressure, generally pressure effect is not there. The slight effect will be there. No more solute can be dissolved. That can be called saturated solution. Next, there exists an equilibrium between dissolved solute and undissolved solute molecules in the solution is called saturated solution. Okay, there will be equilibrium between what happened like this here. Dissolved solute and what happened undissolved solute. In the saturated solution, equilibrium will be there. So dissolve will convert undissolved, undissolved convert to dissolve like that. Equilibrium will be established like this. Solvent holds as much of solute as it possible at that temperature. Undissolved salt remains in the flask. This simple thing only. A dissolved solute is in dynamic equilibrium with solid solute particles here. Whenever it is saturated solution, what happens? Solute, isn't it, will in equilibrium with what happened? Undissolved solute particles here. Dynamic equilibrium means you have studied in the 11th class only. Whenever what happened, two things what? Changing simultaneously. That is called what? Equilibrium actually. When a solid solute is added to the solvent, some solute dissolves, which is called dissolution. What is the meaning of dissolution, beta? Solute dissolving in the what? Solvent is called dissolution. Opposite to this one is called crystallization. Crystallization means what happened? Opposite to dissolution. The solute which is dissolved in the what? Solvent, that is again converting into solute here. That means solution is changing into what here? Solute plus solvent. This is called what actually? Crystallization. Okay, solution converting into solute plus solvent is called crystallization. And what is dissolution? Conversion of solute plus solvent into what actually? Solution is called what actually? Dissolution. Now these two things are taking place, isn't it? Simultaneously. That means dissolution and crystallization both are taking place simultaneously in what? Dynamic equilibrium. Formation of solution, formation of solute plus solvent, both are taking place simultaneously. That is nothing but what? Dynamic equilibrium. So here I am adding some salt to the solvent actually. I am adding some salt to the solvent. Now dissolution took place here. Even somewhat happened, molecules will be there which are unable to dissolve in the water. Now you see, this one is what? Dissolution, and this one is what? This is dissolution. This is what? Crystallization. Now both are taking place simultaneously. This is called what actually? Dynamic equilibrium. When the process of dissolution, crystallization started to occur at the same rate, simultaneously means same rate, under such conditions, the number of solute particles going into the solution is always equal to what? The number of solute particles separating from the solution. This is what? Crystallization, and this one is what? Dissolution. So this is what actually dynamic equilibrium. How many moles are actually what happened? You are dissolving in the solvent, and how many moles of solute coming from the solution, it will be same. That is what, nothing is taking place. In dynamic equilibrium, what happened? Nothing is taking place. When you are standing on the road, that is nothing but a dynamic equilibrium. Nothing is taking place in that. Unsaturated solution means further amount we can add here. A solution in which more amount of solute can be dissolved in the, isn't it, solvent at same temperature and the pressure. This is called what, unsaturated solution. The amount present is less than that means what happened in this case, the solute amount is less here. The amount of solute is what here? Less. That is the reason what happened. It is acting as an unsaturated solution. Now let me see supersaturated solution. A solution in which there is a more amount of solute than that is present in the saturated solution. That means amount of solute is more. Amount of solute is more something like this. Then it is called what? Supersaturated solution. Here we are going to get the PPT. The precipitation will be formed in the solution in the case of what? Supersaturated solutions. Solvent holds more amount of solute. That is the reason what happened. You are getting that precipitation. Like if you observe this diagram, if you am adding like this, when you add what happened, you are getting a precipitation. That means it is not further amount of solute is not dissolving. This is already what happened, saturated solution. This is what type of solution, beta? Saturated solution. Now for saturated, if you add solute to this one, this solute is not dissolving. It is not at all dissolving here, giving a precipitation, something like this. So these are called what? Super saturated solutions. Solubility of gas in liquid. This is there in the syllabus, beta. So you may get questions from this one. Solubility of gas in liquid is a very important one, beta. Henry's law we get in this one is a very important for us in examination point. Now what is solubility of gas in liquid? Do you know that gases also dissolves in water? Like what? Solid dissolve in water. Gases also dissolves in water or other liquids, like solid dissolves in water or liquids. But the amount will be what? Very less. The amount will be less only. Let me discuss about this one. Do you know that most important gas that dissolves to small extent, that is only 5 to 6 ppm in water, and saves the whole flora and fauna under the sea? Isn't it? The aquatic life sustained by oxygen present in what? Water. Because oxygen is dissolved in the water, not very much better, very less only. How much it is? Only 5 to 6 ppm. 5 to 6 parts per 10 lakh parts of water. For 10 lakhs part of water, the 5 to 6 parts is what? Oxygen. That is enough to sustain what? Life under the sea. So this is important of what? Solubility of gas in the liquid here, right? Hydrogen chloride gas, ammonia gas, sulfur dioxide gas, etc. are highly soluble in the water, because hydrogen chloride is polar, water is polar. Ammonia polar, water is also polar. Sulfur dioxide also polar, water is also polar. Therefore, they are highly soluble in the water. But oxygen in water slightly dissoluble. How much it is? I told you. Only 5 to 6 ppm. What is the reason, beta? Why oxygen less soluble and why hydrogen chloride is more soluble, beta?
O2 is non-polar.
Polar is polar and non-polar condition. That means what happened? Polar, non-polar depends upon what happened? Easy liquid, critical temperature, beta. It depends upon what? Critical temperature. Whichever the gases are polar, they are having high critical temperatures. They can be easily liquefiable. Beta. Okay. So easily liquefiable gases are more soluble when you compare to, for example, if I see what happened, ammonia and oxygen, which is easily liquefiable. That means ammonia and both are gas molecules which can be easily converted into liquid, beta. Ammonia. Why? Because ammonia is having more critical temperature. What is critical temperature? The temperature below which the gas cannot be liquefiable. Isn't it? So easily liquefiable gases are more soluble when you compare with what happened? Difficult to liquefiable gases. Solubility of gases is greatly affected by pressure. Now, if you observe what happens, solubility of solids in liquid does not depend upon pressure mostly, but depends upon temperature, some factor. But gases in liquid definitely depends upon pressure and what happened? Temperature. Effect of the pressure, let me see now here. What is the effect of pressure when gas soluble in the liquid? Solubility of gases increases with increasing the pressure. When you increase the pressure, what happened? The solubility of gas will be increases. For example, you take soda water, beta, soda water, isn't it? Soda water you take, beta. Now, whenever, how do they make soda water better? Just generally, do they add gas in water in normal condition, or do they add gas in water at high pressure for making the soda water?
High pressure.
Definitely, what happened? Without high pressure, what happened? You cannot make soda water, right? So at high pressure only, gas will soluble more. So best example is soda water actually. Solubility of gas increases with increasing the pressure. That means we can directly, it is proportional. We know that one actually. So for example, we'll take this example. This is a piston beta. So I put some weight here, something 10 kg, something I put here, a weight here is a piston actually. Now when you put that one, what happened? Here 10 kgs I put here, then I am putting for here 10 kgs and here 10 kgs I am putting here. Then the weight increases, pressure also increases on this solution. Therefore, what happened? With increasing the weight on the piston, solubility of the gas. Now you see these are the gas particles. These are black particles are nothing but beta gas particles are there. All these black particles are gas particles. Now they are not soluble. They are not soluble completely. See. Now, whenever if you observe what high pressure, now they are soluble in the, isn't it, solution? They are completely soluble, isn't it? They are completely soluble in this case. Assume this system to be in state of dynamic equilibrium. Under this condition, pressure and temperature of the gas molecules are entering in the leaving the solution places same here. That means after what, whenever it is same phase we get actually. After that dissolving the gas into the water, even gas particles also will convert into liquefied. Now, concentration of the gas molecules or unit volume of solvent increases, and interactions between the solvent molecules and gas molecules also increases, resulting more solubility of the gas. So, because of interactions between the solute and the solvent, because of high pressure, what happened? The solubility of the gas also increases. Assume that the system is to be in the dynamic equilibrium. Dissolution and the crystallization both are taking place here in equilibrium. Both processes are taking place. Now, when you increase the pressure over the solution, whenever what happened? Dissolution, crystallization, both are in equilibrium. Now, when you increase the pressure over the solution phase by compressing the gas, okay, by using piston, what we are going to observe? As a result, increase in the number of gas molecules per unit volume over the solution. This increasing the pressure of the gas above the solution increases the solubility of the gas until a new equilibrium is reached, and thus it will solubility increases. Now, once you observe this diagram here, it is in equilibrium. Okay. Now, what happened? Both dissolution, crystallization, both are taking place simultaneously. Now, what you are doing, you are increasing the pressure now here. If you observe what happened, you are increasing the pressure here. By using what happened? By using a piston like that here. By putting some weight here. Again, what happens? Solubility is increasing in this case. After increasing the solubility, again equilibrium will establish. Again equilibrium will be established. In which what happened? Dissolution, crystallization will be simultaneously will take place. Equilibrium will be established. That means whenever what happened, you are increasing the pressure, solubility is increasing and establishing what actually equilibrium is establishing between what happened, dissolution and water. This one, crystallization. Now, do you know what happens to the gas when it dissolves in water or any other solvent is heated? So you observe that what some bubbles emanate from water. It indicates gas is escaping in the form of what? Bubbles from the solution. So do you know what happens to the gas when dissolved in water or any other solvent? When you heat, what happens? What? Solubility will decreases. Correct or not? When you heat, what happens? Solubility decreases, and whatever the gas is dissolved in the water will eliminate, escape from the solution in terms of what? Bubbles. Isn't it? Gas escaping from the liquid in which it is dissolved or from solution when it is heated indicates the solubility of the gas decreases. So when you increase the temperature, what happens? Solubility will decreases. For example, if you put soda water in hot conditions, then what happens? The solubility will decreases. The soda water is not tasty for us. But the soda water, if you place in that refrigerator, what happens? Definitely it will very taste because more amount of gas is dissolved in the water. So what I mean to say is that the effect of temperature with respect to solubility, if you observe what happened in gas liquid solutions. What type of solution we are taking here? Gas in liquid solutions. In that case, temperature is inversely proportional to what? Solubility, right? So higher the temperature, if you get, lower the solubility you are going to get actually. If you observe, carbonated soft drinks are more bubble if stored in the refrigerator. Warm lake have less oxygen when you compare in the cool lakes actually. That means carbonated soft drinks are more bubbly if stored in the refrigerator, isn't it? When you are storing the refrigerator water, it will be more soluble in the water. Warm lakes have less oxygen. So whenever what happened, water bodies, if you observe what happened, in that warm water bodies, the sustaining of aquatic life is very difficult. When you compare with what happened, having what? Less temperature. Now this is the graph, if you observe what happened, solubility and the temperature. Now you observe helium, carbon monoxide, oxygen, methane. At low temperature, you observe, at low temperature, their solubilities are very high. Their solubilities are very high. At high temperature, if you observe, at high temperature, this temperature, if you observe, their solubilities are very low. And methane is having more solubility when you compare with helium because of more molar mass. That depend upon molar mass and everything. Interactions, van der Waals force of attractions. Helium is what? Inert gas. Lower van der Waals forces will because of atomic weight here. So that is a different factors actually. So what I mean to say that at low temperature solubility is what? High. At high temperature solubility is what? Less. This is for what? Gas in liquid. An important note, if you observe what happened here. When gas is dissolved in liquid, when a gas is dissolved in liquid, heat is evolved during the process. So this process is calling exothermic process, right? So dissolution process follows dynamic equilibrium, Le Chatelier principle. In exothermic process, the solubility should decrease with increasing the temperature. Let me see this one. I will discuss about this one while taking something. Now I have taken water and I am dissolving the carbon dioxide over in this one. And dissolving the carbon dioxide into this one. Now this process is exothermic. Heat is releasing it. Heat is releasing it. Heat is releasing. When heat is releasing, what happens? Temperature will increases. So when you add carbon dioxide into the water, temperature will increases. The system temperature will increases. Correct? Then if I heat this one, the equilibrium should do what actually? In opposite direction, it will shift actually. That means it should decrease the temperature. It should decrease the temperature. So addition of carbon dioxide increasing the temperature. That means dissolving of carbon dioxide is solubility of carbon dioxide. Dissolving carbon dioxide is increasing the temperature. But when you heat, what happens? It should decrease the temperature. So in which direction the temperature will be decreased beta? In dissolution or crystallization?
Crystallization.
Definitely. Therefore, what happens? Solubility will decrease here. So this we are explaining by what? Le Chatelier principle here. So dissolving of the sometime writing carbon dioxide plus water, we got something carbonated water. We got carbonated water. We got carbonated water. Right? This process I am saying what? Exothermic process. Now, carbonated water converting into carbon dioxide plus water. Which type of process beta? This one? Endothermic process. Okay. Now when you are heating this solution, this carbon dioxide containing water, heat temperature is increasing. Now the equilibrium should decrease the temperature. In which case temperature will be decreased? In endothermic process only temperature will be decreases. In exothermic process temperatures will increases. See, addition of carbon dioxide to the water, temperature is increasing. It's exothermic process. When you are heating the solution, temperature is increasing. Okay, temperature is increasing in surroundings. Therefore, the system should decrease the temperature. System in terms of system is decreasing the temperature. How it will decreases? In endothermic process. What process it is? Conversion of carbonated into carbon dioxide plus water. That means solubility is decreasing. So what I mean to say is that temperature affects the solubility of gas in liquid with reversely. Inversely it will actually, right? Next, we will see the famous law called Henry's law. This is very, very important for examination point of. Henry's law is very, very important for us. In examination point of statement and formula and problems. You have many number of problems are there. In Henry's law, 3 to 4 problems are there. The Henry's law, let me discuss now. Can you tell me who is the first person to give quantitative relationship between solubility of gas and in a solvent with respect to pressure? That is what actually Henry. So Henry has given first representation. What is this Henry's law here? Very simple law it is. At constant temperature, the solubility of the gas in liquid is directly proportional to the partial pressure of the gas. That means if the pressure of the gas is more, then it will soluble more in the liquid. Correct or not? That means the solubility is directly proportional to the pressure. This is called what? Henry's law. Understood better everyone? The Henry's law, simple or not? At constant temperature, the solubility of the gas in liquid is directly proportional to the partial pressure of that gas. It's called what? Henry's law. Understood?
Yes, sir.
Now, what is solubility? Let me see. The mole fraction, how much amount of gas dissolved in the water. The mole fraction of the gas in solution is proportional to the partial. Now, because mole fraction is nothing but beta, amount of the solute. Solubility is nothing but beta. Initially, I told you, solubility means amount of solute dissolved in the water or liquid actually. Amount of the solute dissolved in the liquid is nothing but solubility. Amount is nothing but what? Mass. Mass is nothing but what? Mole fraction. Now we can say mole fraction of a gas. Mole fraction of the gas means how much amount of gas dissolved in the solution. So that is directly proportional to, now we can say, partial pressure. So now we can rewrite this one, mole fraction of the gas directly proportional to the partial pressure of the gas. The partial pressure of the gas in vapor phase is proportional to the mole fraction of the gas in the solution. So Henry's law can be expressed like this. Partial pressure of the gas directly proportional to its mole fraction. For example, partial pressure of oxygen directly proportional to mole fraction of the oxygen. Now, remove the proportionality constant. What we can write? Partial pressure of oxygen is equal to Henry constant. K is nothing but Henry constant mole fraction of oxygen. So we can write like this, where KH is equal to Henry's law constant. Instead of taking the what solubility, what I am taking beta here? Mole fraction I am taking. That is only I am changing here, right? When you draw a graph between partial pressure and mole fraction, definitely we can draw, because it is what directly proportional, we can draw the graph here. Let me see that graph here. Partial pressure of a gas, the gas I have taken HCl, the pressure we are taking in terms of torr here, and mole fraction of the HCl present in the solution. That solution is made up by HCl plus cycle. This is solvent actually. Okay, this is gas, HCl is a gas, this is a liquid. Now what about the mole fraction? Partial, you see. You got a straight line. As amount of HCl gas is increasing in this, the partial pressure of the HCl is increasing. As partial pressure of the HCl is increasing, the amount of HCl is dissolving in the cyclohexane also increased here. Yes, we are getting a straight line actually. Now, if you observe what happened, the solubility of the various gases, helium, hydrogen, nitrogen, oxygen, argon, carbon dioxide, formaldehyde, methane, vinyl chloride, CH2, double bond CHCl is called vinyl chloride. What happened to these type of gases when they dissolve in the water? Now let me see what happened. Let me see this one. Now if you observe what happened, helium gas, if you observe, which has the Henry constant, if you observe, 144, right? Then you take what happened, hydrogen, the Henry constant is 69. But the nitrogen, if you observe what happened, that is 76 here. Nitrogen at high temperature, dissociation constant, that is sorry, K, Henry constant, what happened? Increasing. For oxygen, it is 34. At high temperature, it is 46. So what you observe here, whichever the gases which are having high critical temperature, easily liquefiable gases, whose Henry's law constant is what? Less. Easily liquefiable gases which are having high critical temperature, they are having less Henry's law constant. One thing you are observing, see, oxygen, less liquefiable gas. Carbon dioxide, more liquefiable gas. Now, easily liquefiable, that means easily liquefiable gases like carbon dioxide is having very less Henry's law constant, whereas difficult to liquefy gases are having what? More Henry's law constant. The first statement. Second statement, when you increase the temperature from 293 to 303, 10 degrees Celsius, if you increase, what happened? The KH is what happened here? Increasing. That means second statement, first statement, if you observe what happened, easily liquefiable gases are having what? More solubility. And second statement, when you increase the temperature, solubility is decreased. That means KH is inversely proportional to what? Solubility. Right? The Henry's law constant is inversely proportional to solubility. So, this is a statement we can derive from these two tables actually. Soft drinks and soda water, carbon dioxide is passed under high pressure and sealed by, what is the reason? Based on Henry's law only. To increase the solubility, what happened? They are dissolving, the carbon dioxide is dissolving in the water at which pressure beta? High pressure. Why they are sealing? Because the gas could not escape from the solution actually. If you observe what happens, scuba divers have high concentration of dissolved atmospheric gases in blood. Why? What is the reason here? So I will explain this one, what happened later. Once we complete this problem, I will explain this one. Later we are going to explain this one. Since I will scuba divers, I will explain later. Can you give the answer better? Henry's law applicable at constant?
Temperature.
Temperature.
I better do problems here. That application part we will discuss later. I will do problems by using what happened? Henry's law. What is Henry's law? Pressure of the gas, partial pressure of the gas, directly proportional to what? Mole fraction of the gas actually. Correct? Based upon this formula, let me take some problems over here. If nitrogen gas bubbled through water at 293 Kelvin temperature, how many millimoles of nitrogen gas dissolve in 1 liter of water? They're asking how many millimoles of gas will dissolve in the water. Assume that nitrogen exerts partial pressure. The partial pressure of nitrogen is given 0.987 and the Henry law constant is given 76.48. Now they given what actually? Partial pressure. How much they given? 0.987 bar. And one more they given here. Henry's law constant 76.48 Kelvin they give. Now what we have to calculate? Mole fraction of the gas we have to calculate. From that, how much amount of gas, nitrogen present in the 1 liter of water. So these things you have to calculate. So P is equal to KH into X here. Pressure is equal to 0.987. They given this pressure here. How much it is? 0.987. From the data it is given. KH is also given. How much it is? 76.48. So 76.48 you got here. Now based on this, isn't it? You can convert that one into what happened? Kilo, you can convert into kilobars, you can convert into bars like this, isn't it? Right? Because here it is given in terms of bar, it is given in terms of kilobar. So convert into bar only. This one also convert into bar, right? Both you should be there in the, otherwise you convert this one into kilobar. Anything is better. Now based on this, mole fraction is equal to what? Partial pressure of the gas by Henry's law constant. So 0.987 by something like this. Okay, this is by this one. Now we got mole fraction how much better? After doing this one, This is a mole fraction 1.29 into 10 to the power of minus 5. Does it have any units beta? Mole fraction? Does it have any units?
No,
No.
sir.
No, sir.
Now we got mole fraction beta. Now mole fraction is equal to what? I want to calculate mole fraction of what we are calculating beta? Nitrogen we got. Mole fraction of nitrogen.
No, sir.
1.29 into 10 to the power of minus 5. This we got actually. But what they are asking, how many moles of nitrogen present in the 1 liter water they are asking. Now what is the formula of mole fraction of nitrogen? Number of moles of nitrogen plus number of moles of nitrogen plus number of moles of solvent is what here? Water. Now they are saying 1 liter of water. They are saying 1 liter of water. 1 liter means what? 1000 ml. 1000 ml here. Now what is the weight of 1000 ml beta in grams? Density of water is equal to what beta? Density of water will be what? 1. That means 1 gram of water will contain 1 ml. Based upon 1000 ml contains what is the weight beta? 1000 ml
1000 gram.
1000 grams. So the weight of 1000 ml is equal to 1000 grams. Based upon we can calculate number of moles of water, correct or not? So how much weight we got? 1000 grams for 1000 ml. So substitute here, weight is equal to how much here? 1000 ml. Molecular weight is how much? 18. Now based on this, how much we get? 15.55 we get. That is the number of moles of water. How much we got? Number of moles of water, how much we got? 55.5 moles we got. Now 1 liter of water always contains 55.55 moles actually. Based upon this formula I got. Correct? Now we got number of moles of water, how much beta? 55.55. But the gas we are dissolving is very less, no? Because the solubility is very less. When I told you just now, nitrogen gas, oxygen gas, the solubility is very, very, very less. Correct or not? That means if I add something from 0.01 to this one, is it change here? So that is the reason you neglect this one. You neglect this one. Now mole fraction of nitrogen. Now mole fraction of nitrogen, you see this one. The mole fraction of nitrogen, otherwise I will write here. The mole fraction of nitrogen is equal to number of moles of nitrogen divided by what happened? Number of moles of what? Water. Shall I write like this? Because here this one I have neglected. This value I have neglected here. Because this is what? Dilute solution, very dilute solution. The amount will be very less, maybe 0.001. So adding 0.01 to 55.5 is very less only. So that is the reason I am doing what happened. Mole fraction of nitrogen is equal to number of moles of nitrogen by number of moles of water. How much we got mole fraction of nitrogen beta? 1.29 into 10 to the power minus 5. 1.29 into 10 to the power of minus 5 is equal to number of moles of nitrogen. Water number of moles we got 55.55. Now cross multiplication, number of moles of nitrogen is equal to 55.55 into 10 to the power of minus 5 into 1.29. Now we got number of moles, but they are asking millimoles. Convert that one into millimoles by multiplying it 10 to the power of minus 3. Will get the answer. In this way, what happened? We are going to get the answer. And 716 millimoles. Very simple problem, but lengthy it is. Understood, beta? Everyone? Everyone understood?
Yes, sir.
Right. Okay. And that this is about the Henry's law, beta. You do some more problems are there. More problems I will show you. Do that one. And whatever the applications of this Henry's law, we'll discuss tomorrow. The applications of Henry's law, we'll discuss tomorrow. I think we have completed this one. Example 2.4 we have completed. This one we completed actually, correct? Now what you have to do? Homework. I'll show that. This one you can do, Henry's law, 2.6 and 2.7. Try to do this 2.6 and 2.7 today itself. Complete this 2.6 and 2.7 today itself. And tomorrow we'll complete what? Henry's law application and remaining topics. Next topic we'll discuss. Okay. So this is the homework for you. 2.6, 2.7 is the homework for you. Here you have to calculate the Henry's law constant And here you have to calculate the Henry's law of constant is given. Calculate the quantity of carbon. Again, same weight of carbon. In the previous problem, we calculated the number of moles. Now here we can calculate the in terms of grams actually. If you know the mole, you can convert into grams. Okay, right?